You know how you can plug an Ethernet cable into a switch and it just works? It really feels like magic, doesn't it? But behind that simple little box with the blinking lights, there's a seriously smart process going on that stops our local networks from turning into total chaos. So let's pull back the curtain and see how the humble but honestly brilliant network switch actually works.
I mean, really think about it for a second. In your office or even at home, you've got dozens of devices all trying to talk on the same network. So when you hit print, how does your computer manage to send that file only to the printer? Or how does your Xbox get that perfect lag-free connection to your router when your roommate is streaming a 4K movie right next to you? Well, that's the whole problem the switch was designed to solve. It's basically the high-speed traffic cop for your local network.
To really get what a switch does, we first have to meet our main character, this little packet of data called an Ethernet frame. This is the basic package for all communication on your local network. Just think of it like a digital envelope. It's carrying your data inside, and just like a real envelope, it needs a to address and a from address to get where it's supposed to go.
Now, what's pretty cool is that these digital envelopes have to follow some rules. For an Ethernet frame to even be considered valid, it has to be at least 64 bytes. Anything smaller than that gets labeled a runt frame. And you can think of that like a letter that got shredded in the mail sorter. It's useless, you can't deliver it, so the system just throws it away. It's a simple, built-in quality check that keeps broken bits of data from jamming up the works.
Okay, so how does this digital envelope find the right person, the right device? Well, the secret is something called a MAC address. It's a unique, permanent ID that's stamped onto every single device that can connect to a network. It's kind of like a digital fingerprint that, in theory, can never be changed.
Let's break that down. A MAC address is a 48-bit number, and you'll usually see it written out in hexadecimal. It is literally burned into the hardware of the network interface card, or the NIC. That's the little chip inside your computer that has the physical Ethernet port on it. This is what we call a Layer 2 address, which is just a fancy way of saying it's for talking to devices on the same local network.
And here's how they make sure that every address is unique across billions and billions of devices. It's actually a pretty clever system. That 48-bit address is split right down the middle. The first half is called the Organizationally Unique Identifier, or OUI. That part is given to a specific manufacturer like Apple or Intel. Then, that manufacturer uses the second half to give each device they make its own unique serial number. It's a simple, elegant way to make sure no two devices on Earth should ever have the same MAC address.
So our Ethernet frame now has the destination MAC address stamped on it. It leaves your computer, travels down the wire, and arrives at the switch. And this is where the magic really starts to happen. See, a switch isn't some dumb box that just blasts data everywhere. No, it's a dynamic, thinking device that actively learns the layout of its own network.
The entire brain of the switch is really just one thing, a dynamically built map called the MAC address table. Now, if you're talking to network engineers, you might hear them call it a CAM table. But the most important thing to remember is this. When you first turn a switch on, that table is completely 100% empty. It knows nothing. It has to learn everything from scratch.
And it does that learning with a super simple two-step logic that it applies to every single frame thousands of times a second. First, it learns. It looks at the source MAC address where the frame came from, and it makes a note of which physical port it arrived on. Then, second, it forwards. It looks at the destination MAC address and checks its map to figure out where to send it. Learn, then forward. That's the whole game. So let's watch it happen. A computer with a MAC address ending in 6816 sends a frame, and it comes into port 1. The switch sees this, checks the source address, and has this little light bulb moment. Aha! I now know that this device lives on port 1. And boom, it adds an entry to its table. A little later, a printer with a MAC ending in 6817 sends something into port 4. The switch does the exact same thing. It adds a new line to its map. It's constantly, dynamically building a picture of its local neighborhood.
Okay, so the switch is busy building its map. Now, let's look at how it actually uses that map to make an intelligent decision. This is the logic that makes your network so incredibly fast and efficient.
This right here is the critical decision point. A frame arrives. The switch looks at the destination MAC address. If that address is in its map, perfect. It knows exactly where to send it. It forwards the frame out of that one specific port, creating a private little conversation. But what if the destination isn't in its map yet? Well, then the switch has no choice. It has to flood the frame out of every single port, basically shouting, "Hey, who is this for?"
We call that an unknown unicast.
Now, you don't want to confuse flooding with a broadcast. They're different. Sometimes a device actually needs to talk to everyone on the network at the same time. And to do that, it uses a special destination address, all Fs. When a switch sees a frame addressed to all Fs, it knows the sender's goal is to shout to the entire room, and it does its job and sends that frame out to every single device connected to it.
So that's the core logic. But of course, modern switches have a few more tricks up their sleeve that make them even faster and more reliable. Let's look at a couple of these pro features that are the reason your network, well, just works. When it comes to forwarding frames, switches have two main strategies, and it's really the classic trade-off between being fast and being accurate. With store and forward, the switch waits to receive the entire frame, checks it for errors, and only then sends it along. This is super reliable, and it's crucial for things like voice calls. Then you have cut-through, which is all about raw speed. As soon as the switch reads the destination address at the beginning of the frame, it starts sending. It's way faster, which is awesome for gaming, but you run the risk of forwarding a corrupted frame.
Here's a problem that used to drive network technicians absolutely crazy: duplex mismatch. Imagine you're on a phone call where you can talk and listen at the same time, but the person on the other end can only do one at a time. It would be a total mess of you talking over each other. That's exactly what can happen on a network, and it causes huge performance hits. The modern solution is auto-negotiation, where the switch and the device have a quick chat and automatically agree on the best settings, preventing this network killer before it even starts.
And here's another great example of that built-in smarts, AutoMDIX. I know it's a mouthful, right? But what it does is actually simple and genius. See, back in the day, you had to use very specific types of Ethernet cables, either a straight through or a crossover cable. If you used the wrong one, your connection just wouldn't work, period. AutoMDIX lets the switch port automatically figure out what kind of cable you plugged in and adjusts itself. It's one of those amazing little features that has saved technicians countless hours of headaches.
So when you boil it all down, it really comes back to this one simple idea. A switch is a specialist. It lives and breathes at layer 2 of the network. Its entire world begins and ends with MAC addresses. It doesn't care about IP addresses, it doesn't know about websites, and it has no idea what's inside your data. Its only job is to build its local map and deliver those digital envelopes as fast and as accurately as possible.
And that really leaves us with one last question. If the switch is the super efficient mail sorter for one single office building, making sure every letter gets to the right desk, what happens when you need to send a letter to a completely different city, across the country? Well, that local mail sorter can help you. You're going to need a different kind of device, one that operates at a higher level with a much, much bigger map of the world. And that, my friends, is where a router comes in.